Hello friends, welcome back to this series where we go through and explain the book on quantum mechanics by Weinberg. In this lecture, we continue our discussion on the general theory of rotations and angular momenta. Last time, we have shown how to construct an angular momentum multiplet by using just the rotation algebra, that is, the commutation relations involving all the components of angular momentum. This is a set of states that carry the same angular momentum quantum number j and differs from each other only by the third component, labeled by the number m. These are just states of a single angular momentum operator. This operator may be attached to a system, or in our case, to a particle. Today, we examine the possibility of two angular momenta, which may belong to two separate particles. Or it could be two different types of angular momenta belonging to the same particle, like its orbital angular momentum and spin. One representing the motion of the particle, and the other its internal states. The question we now ask is, what would be the eigenstates of the sum of these two angular momenta? We can make this more general by letting the two sub-angular momenta to be arbitrary, J prime and J double prime. For this total angular momentum, we can also construct a set of eigenstates which forms multiplets, each labeled by a quantum number j. This is again the direct consequence of the rotation algebra satisfied by the total angular momentum j. The same thing applies to both the constituent angular momenta j prime and j double prime, and they each have their own set of eigenstates forming separate multiplets, as they too satisfy the rotation algebra. They are independent degrees of freedom in the sense that they commute with each other. Somehow, we should be able to deconstruct the eigenstates of the total angular momentum in terms of the constituent states. Note that since J prime and J double prime commute, they must share eigenstates. These are simply the tensor product of their individual eigenstates. Our task now is to deconstruct the total angular momentum states Jm in terms of the product states of the constituents for fixed values of J prime and J double prime. This constraint makes sense since one of the first problems we will solve with this formalism is to figure out how the spin of the electron managed to split an atomic level with orbital angular momentum L. With J prime and J double prime fixed, we can hide these quantum numbers and simplify our notations. An obvious result comes from applying the third component of the total angular momentum to these product states. They are just the eigenstates of J3 with quantum numbers that are just the sum of m prime and m double prime. So are the total angular momentum states Jm. So if we are to construct these states in terms of the product states, we will need to impose this condition. Out of the entire set of states that satisfy this condition must come Jm. The product states are chosen from the usual intervals that constrain m prime and n double prime for fixed values of J prime, J double prime. For example, the values of m prime in this interval is given by, where the possibilities of integer and half-integer values of angular momentum are both allowed. See Lecture 20 if you're unfamiliar with these results. We begin by expressing Jm in terms of the product states m', m', from the bases in the red box. These unknown coefficients C's are what we need to solve. The sum over m' and n'' satisfies the constraint in the blue box. Let's review all the quantum numbers once again to make things explicit. We remind ourselves that the product states also carry the quantum numbers J' and J" by writing this in the subscript of the expansion coefficients C. The indices that are summed over are underlined green. The rest are constant within the sum. Let's switch back to this more concise form. These expansion coefficients are known as the Clebsch-Gordan Coefficients and will occupy us for much of this lecture. From a symmetry standpoint, these Jm states are more relevant to the energy states of the rotationally invariant Hamiltonians that we are interested in, because they are the eigenstates of the total angular momentum J, which is the true generator of rotations and not the subangular momenta J' and J'. Thus only J commutes with H, and they share the same eigenstates. That is to say, only the Jm states could be energy states, which are the subjects of atomic spectra. As noted earlier, because J' and J" are subangular momenta, and therefore not the actual generators of rotations for the full system, they might not commute with H, which is the total energy of the system. But H can certainly contain rotationally invariant terms like their dot product. Because J' and J" are vector operators and rotate like vectors, this implies that their square must be invariant under rotations and commute with J. The result is that the following operators all commute with each other. The operators underlined blue commuting with those underlined green means that the total angular momentum states Jm also carries the quantum numbers J' and J'. This is therefore consistent with the right-hand side of this expansion, as the product states also carry these quantum numbers. Not to make too fine a point, only one component of J can be chosen in this set. Note that even though we shall hide these additional quantum numbers in the states Jm most of the time, for simplicity's sake, they are physically important, because not all states with the same total angular momentum are equivalent. They may still differ by their constituents, which is why we still keep the subscripts in the expansion coefficients. We now explain a systematic way for calculating these Clebsch-Gordan coefficients, and on the way, we will be able to figure out in a general way, given values of J' and J', what are the possible values of J that will come out of this composition. For a start, we know that the maximum value of m' is J', and for m', J'. This immediately implies that the maximum value of m for the total angular momentum must be equal to J' plus J'. Since there is only one possible product state that could take this value, namely the one with m' equals J' and m' equals J'. This must also be the total angular momentum state with J equals J' plus J', as m is at its maximum value. That is, This must also be a highest weight state. What this means is that if we apply the raising operator as defined in the red box for the total angular momentum on this state, we must get 0. This makes sense as there are no more states with higher values of m within this multiplet. J plus is also just the sum of the constituent raising operators. J plus prime plus J plus double prime. Let's check if the identity above is true by applying these operators to the product state. Indeed, both contributions in the sum are 0, as the raising operators act on their respective highest weight states in the product. Let's look at the coefficient C for this simple case. Obviously, there's only one of them that are non-zero, with value equals 1. This corresponds to J equals J prime plus J double prime, and M equals M prime plus M double prime, which are enforced by these two deltas. You should treat M prime and M double prime as parameters that are fixed, with J and M as variables. The two Kroneckers delta make much more sense when read this way. This is the convention in Weinberg's book. Let's substitute in the fixed value of M prime and M double prime from the right hand side of this equation. Thus we have solved our first Clebsch-Gordan coefficient, which belongs to the highest weight state of the J equals J prime plus J double prime total angular momentum multiplet. As usual, applying the lowering operator to this state will give us the rest of the multiplet. But J can take other values. That is to say, there's actually more than one total angular momentum multiplet that can be composed out of the product of a J prime and J double prime multiplets. We can easily see this by counting the states in both cases. For the multiplet J equals J prime plus J double prime, the number of possible m's is just 2 times J prime plus J double prime plus 1. For the product states, the total number of states is just the product of the number in each individual multiplet, which are in these intervals. This can be written as: we can see that this number is in excess of the earlier number by 4j prime j double prime. Therefore, the number of states that are in the J equals J prime plus J double prime multiplet cannot account for all the states that are contained in the product. Now let's find the rest of these states. We can derive the rest of the states in the J equals J prime plus J double prime multiplet simply by applying the lowering operator J minus. This procedure is straightforward, and we shall only take one step below the highest weight state as an example, which is the case of m equals J prime plus J double prime minus 1. The spacings between adjacent values of m must be 1 as a result of the rotation algebra, as we have shown in the last lecture. This lower state is proportional to J minus acting on the highest weight state. We shall work out the normalization of this state later. Let's proceed by expressing both the lowering operator and the highest weight state in terms of their constituents. Then match each operator to their respective component states. The calculation for the prime and double prime multiplet is identical. We can use the formula in the green box below, derived in the last lecture. This formula is general and gives the effects of the raising and lowering operator on any state in any multiplet. For the first term, m prime is lowered one step, and for the second term, m double prime. Alpha plus minus is the normalizing factor that results from such operations and is derived using the rotation algebra in the last lecture. The alphas for the prime and double prime cases are identical. Simply interchange j prime with j double prime. Let's evaluate just the prime case using the expression below. For the double prime case, just replace j prime with j double prime. Let's substitute all these back into the expression above. Thus we have the result of j minus acting on the highest weight state. Let's simplify the notations for the underlying states further. And ignore the overall factor for the moment. This is the state that is one step below the highest weight state in the j equals j prime plus j double prime multiplet. This state is easily normalized by dividing by the square root of j prime plus j double prime. Let's represent the highest weight state in the j equals j prime plus j double prime multiplet by a yellow box and the second highest weight by a white box. Notice that this lower state is supported by just two basis states, which are the results of either descending in the prime multiplet or the double prime multiplet. This means there's room for just one more state that is orthogonal to the second highest weight state in this subspace, where m equals j prime plus j double prime minus 1. It is easy to see that there cannot be more than two basis elements with this quantum number, since either the prime or the double prime state is at its highest weight. And to maintain this value of m, we must raise one weight in order to lower the other, which cannot be done further beyond these two states. We denote the second state in this subspace by a yellow box in anticipation of the fact that it is also a highest weight state and is equal to 0 under the action of j plus. And this must necessarily be the highest weight of a new multiplet, because there can only be one highest weight state within the multiplet, as we have shown in the last lecture. Furthermore, since this is the only other state that could have this value of m, it must be a highest weight state with the same value for j. This is the start of a new multiplet, j equals j prime plus j double prime minus 1. Let's check if this state goes to 0 if we apply the raising operator. We shall label this as psi for now. By definition, psi is orthogonal to the second highest weight state in the j equals j prime plus j double prime multiplet. Comparing with the state above, we can easily construct psi. What we claimed earlier is that psi is in fact the highest weight state of the new multiplet, j equals j prime plus j double prime minus 1, and must vanish under the action of j plus. Let's check. Starting with the orthogonal condition with the second highest weight state of the first multiplet. Taking the complex conjugation of this equation, we have we are very close to what we want to show, which is underlying rate. We just need to take out this state. That is to say, what we need is for this bracket to vanish for any state Jm. The only non-trivial cases we need to consider is those states with the correct m, since for psi, m equals j prime plus j double prime minus 1. Under the action of j plus, only those states with m equals j prime plus j double prime will survive. Although we allow j to take any value, the only way m could be accommodated is for j to take the value above, since it is the maximum value for j itself. But we have shown that this is 0. Therefore, psi is indeed the highest weight state of the new multiplet. Now that we know there are at least two multiplets for the total angular momentum, an obvious question to ask is, are there any more? Let's generate the rest of these two multiplets by applying the lowering operator. M changes by increments of 1 to the left, since it is the sum of m prime and m double prime, both of which are spaced in units of 1. While j decreases in units of 1 downwards, as it is just the maximum m in each multiplet. Once again, we claim that apart from these two white boxes, there remains only one more state, a highest weight yellow box orthogonal to them, that share the same value of m equals j prime plus j double prime minus 2. We now repeat the argument we have used before. If this state is truly the only remaining one with this value of m, and from the diagram, it is obvious that the other states sharing this value are not highest weight states, then the new state must necessarily be a highest weight state. Otherwise, we will be missing a state in the Jm basis. The key point that our argument depends on is the fact that every time we descended one step by applying J minus, there remains only one new state which is orthogonal to the others with the same value for m. We shall prove this in a minute. Let's fill up this diagram to get a more complete picture. As we descend to the right, to the lowest weight, we get more multiplets going downwards with decreasing j until we get to its minimum value. At the same time, the number of states with the same value for m increases by 1 with each step until the multiplicity of m reaches its maximum value. We already know that the maximum value for j is j prime plus j double prime. It now remains for us to figure out its minimum value. This maximum multiplicity holds the answer. To calculate this number, we start with the absolute highest weight, where m prime equals j prime and m double prime equals j double prime. From here, we begin our descent. This can proceed in two ways. Either we go down by the prime multiplet, branching to the left through the action of j minus prime, or by the double prime multiplet to the right, with j minus double prime. As we have seen earlier, going down one level brings us to a subspace spanned by only two basis states with the same value of m, so the multiplicity is 2. We can keep going with the same branching options available. At the third level, Notice that some states from the branching are identical, and so are merged. It is obvious that at each level of descent, the multiplicity increases by 1. This is just what we say we will prove earlier. Eventually, we have to stop either when we hit the lowest weight state in the prime multiplet on the left, if j prime is less than or equal to j double prime, or when we reach the lowest state in the double prime multiplet on the right, if j prime is greater or equal to j double prime. Without loss of generality, we shall assume that the second inequality is true. This lowest weight state has m double prime equals minus j double prime. The maximum multiplicity that we are trying to get is just the number of squares on this last level. Since the triangle is symmetric on all sides, this is also equal to the number of squares on the right side, which is just equal to the number of values for m double prime. That is 2j double prime plus 1. Going back to the multiplet diagram, we are now in the position to find the minimum j. This is the value that corresponds to the last row, because the maximum multiplicity of m is equal to the number of levels. The number of steps it takes to descend to the last level is just this number minus 1, which is 2j double prime. Thus the minimum j is equal to the maximum j prime plus j double prime minus 2j double prime. This is just equal to the magnitude of the difference between j prime and j double prime, considering that we have taken j prime to be greater or equal to j double prime. Thus we have found the minimum value for j, and also its entire spectrum. This multiplet diagram provides a complete algorithm for evaluating the total angular momentum states Jm, starting with just the absolute highest weight state, then using the lowering operator and the orthogonality conditions. We are now ready to count the total number of Jm states that are constrained within these intervals, and check if it agrees with our earlier counting of the product states that are the constituents. The total number of states for a fixed j is just 2j plus 1, then summed over j within this interval. We can write this as the difference between two sums, the first from j equals 1 to j prime plus j double prime, which is the upper limit of the sum on the left-hand side, and the second from 1 to the absolute value of j prime minus j double prime minus 1. Both of these sums started from 1 and ended on different values, which we label by n. We can now apply the formula in the yellow box to the two sums in the red box separately. For the first, n equals j prime plus j double prime. And for the second, the difference between these two terms gives. Then the remaining terms. Let's write this term as a product so that we can complete the square for the right-hand side. Thus these two sets have the same number of states, as they should, because they are just different bases for the system of two angular momenta, with the Jm states labeled by the total angular momenta and the product states by the constituents. Let's examine the normalization of the states Jm. The product states, which form its bases, are also normal. The tilde just means quantum numbers with different values. Similarly, the Jm states are also orthonormal, since they form an alternative basis. To tidy up this clutter of indices, we switch to a simplified notation. The indices Jm is replaced by n, which is some sort of unified index, while the pair m' and m" is replaced by a. The Jm states are represented by the symbol phi, and the product states by phi prime. The elements of the square matrix C and A then represent the Clebsch-Gordan coefficients. Let's apply the green box to the blue box. Then use the yellow box. We obtain a relation for the coefficients C. This can be written in the form of a matrix multiplication. The second factor is simply a Hermitian conjugate. Thus the matrix C multiplied by its Hermitian conjugate must give the identity. If we take the determinant of both sides of this equation, we get. Here's how we get this term. This implies that the determinant of C is non-zero, which means that C is invertible. Let's find C inversed. By the equation above, this is also equal. Multiply by the inverse from the left, we have. A key point to note here is that the inverse could be applied to either side of C. Therefore, C dagger C is also equal to the identity. While previously, we have deduced that C times C dagger equals identity from the orthonormality of states. Using this new equation, we can invert the relation between phi and phi prime. First, we revert this back to its components form. Thus we now have phi prime in terms of phi. This translates into the constituent product states expressed in the basis of the Jm states. All thanks to these identities that are satisfied by the coefficients C. Let's work out one last example of the Clebsch-Gordan coefficients. This one will be less trivial than the previous. These are the coefficients associated with the m equals j prime plus j double prime minus 1 subspace. We can evaluate these coefficients with the help of the two Jm states in it, which are solved earlier. Let's recall the convention for writing these coefficients. M' and M" are taken to be fixed parameters, while J and M are variables. And we must have a delta symbol to maintain the condition M equals M' plus M", together with some further requirements. Of course, we must have M equals J' plus J" minus 1. There are two ways for this to occur. Either M' equals J' minus 1 with M" equals J", or M' equals J' and M" equals J" minus 1. Let's look at the coefficients associated with the first way. Within these curly braces, the conditions for J will be enforced that would correspond to the two states below. J could be equal to J' plus J", as in the first state, with this coefficient. J could also be J' plus J" minus 1, as in the second state, with this coefficient. Thus we have the Clebsch-Gordan coefficients for M' equals J' minus 1 and M" equals J". What about the ones for M' equals J' and M" equals J" minus 1? M is unchanged, hence the delta in front is still the same. Now for the conditions for J. Again, J equals J' plus J" with this coefficient, or equal J' plus J" minus 1 with this coefficient. Thus we have all the coefficients for the M equals J' plus J" minus 1 subspace. This completes our example of the Clebsch-Gordan coefficients. They can be found collected in tables in most textbooks on quantum mechanics and also in its Wikipedia entry. After all these general discussions, let's move on to more concrete examples. But first, let's restore all the hidden quantum numbers in these states and summarize our results. Let's apply these to the case of the atomic orbitals, which are the states of an electron in an atom, with L as its orbital angular momentum and S its spin. The prime system is the orbital part, while the double prime is spin. Changing notations according to the blue box, we have the electron is spin half. This is a fixed intrinsic property of the particle. Notice that when L is non-zero, L minus half is equal to its magnitude, since the orbital quantum number are positive integers. So there are two states within this interval, one with J equals L plus half, and the other with L minus half, forming a doublet for a given L. Whereas for L equals 0, there is only one state, a singlet. Now consider the energy of an electron within an atom. We will need to include the principal quantum number n. Recall that in lecture 19, we are trying to explain the appearance of two energy levels instead of one for a given L, where we argue from rotation symmetry that these energy splittings cannot be explained by ML, which are the projections of orbital angular momentum along the third axis. Hence the need to introduce electron spin. The most direct way to do this is to attach an angular momentum state associated with this spin and choose s equals half to give the doubler. This seems to suggest that the energy splitting is the result of the spin projections having two different energies, which is plainly wrong since this would contradict our earlier argument about rotation symmetry. As ms is not invariant under rotation, and so cannot influence an energy that is invariant. But on the other hand, J is invariant. Thus the correct way to introduce electron spin to explain the energy doubling is through the Jm states, in which spin is incorporated into the total angular momentum. The results in the green box correctly explain the observations we have made in Lecture 19 about the doubling of atomic spectral lines. If we look at just the basic Bohr's model, which takes into account only the Coulomb interaction between the electron and the nucleus, the energy of the electron depends just on n and is independent of any angular momenta. To make our theory of energy splitting work, we need to include the interaction between the magnetic field generated by the motion of the electron, represented by its orbital angular momentum, and the magnetic moment carried by its spin. This must take the form of a dot product between the two vectors to preserve rotational invariance, since we don't expect the atom to have a preferred direction. This is known as the spin-orbital coupling. Its form is also suggested by the interaction of a magnetic moment with a magnetic field, as described by classical electrodynamics. The idea of an electron carrying a magnetic moment comes naturally, since the physicists back then already tried to picture the electron as a spinning charged sphere. This goes to show that sometimes even a naive picture can give useful results when there are empirical data to guide you along. Just be aware that this expression is not quite the full story. The coupling strength represented by lambda is actually an operator and not just a number. Furthermore, this operator may not commute with the rest of the Hamiltonian, which makes solving for its eigenstates difficult and must be approached with the approximation methods to be introduced in Chapter 5. For now, let's just treat lambda as a small number. This will make sense in the next chapter. With this assumption, we can see that the newly added interaction actually commutes with H0 and therefore share the same set of eigenstates. To make this clear, let's write L dot S in this form, where the equation J equals L plus S is used. It is now obvious that the shared eigenstates between H0 and the angular momenta are also the eigenstates of this operator. Now we have the energy shift from Bohr's values due to spin-orbital coupling. So for a fixed n and a given L with spin half, the splitting of energy is due entirely to the dependence of the energy shift on J. This splitting, where two closely spaced energies are found instead of one, is known as the fine structure. Let's move on to a concrete example, the hydrogen atom. We shall look at the transition of an electron between two states, both with n equals 2 and L equals 1. They differ only by the quantum number J. Note that we are using the standard spectroscopic notation on the right. These values of J form a doublet. The transitional energy between these two levels is given by this is about 6 orders of magnitude, smaller than the energy separation between states that differ by their principal quantum number. One thing you ought to know is that the spin-orbital coupling is just part of the contribution to the fine structure. There is actually a correction due to the relativistic effect of the electron's motion. It turns out that the two effects add up to give only a dependence on J. Thus the energy shift is just some function of J. We shall work this out in details in the next chapter. Anyway, this does not change our conclusion that the fine structure splitting is still due to the doublet of J, and the transition energy between two states with the same quantum numbers n and l but with different J is still non-zero. However, when we have two states differing only by L with the same N and J, this formula gives the same energy for both states and cannot explain any non-zero transition energy between them. For the first state with L equals 1 and spin half, the values of J are, while for the second state with L equals 0, both of these cases contain J equals half, which are the states we are considering in the above transition. Thus, in order to explain the energy of this transition, we need to consider additional effects on top of the spin-orbital coupling and the relativistic effect of electron motion. This is the effect of the vacuum of the quantized electromagnetic field. You can think of it as the shift of the electron's energy as it absorbs and emits virtual photons. The photons can't be real, as we are after all dealing with the vacuum. All these will become clear in later lectures when we get to the quantum theory of the electromagnetic field. The result is this transition energy between the two states with same quantum number J but different L. This is known as the Lamb shift, after its discoverer Willis Lamb. Compare this with the energy due to the fine structure. This effect is one order of magnitude smaller than the fine structure. There is yet another magnetic interaction in an atom that is very similar to the coupling between the orbital and spin angular momenta of the electron. This is the interaction between the spin magnetic moment of an electron and the field of another magnetic moment due to the spin of the proton. Naturally, this is known as the spin-spin coupling. This gives rise to the hyperfine structure of the atomic spectra. As the name suggests, it is one order of magnitude smaller than the fine structure and on the order of the Lamb shift. In these expressions, we have assumed some kind of proportionality between the magnetic moment of a particle and its spin. Let's demonstrate this by a hand-waving argument. But note that all these interactions arise naturally in the relativistic quantum theory of electromagnetism, that is, quantum electrodynamics, the first successful quantum field theory. Nothing needs to be put in by hand, as we are doing now. First, let's look at a charged particle. Imagine that this is actually a loop of electric current with charge Q and radius r. This current has the usual definition for a one-dimensional loop. It is the charge density of the loop, Q divided by its length, multiplied by the velocity of the charge, which is the angular velocity omega times r. If we assume that the mass of the particle is also spread uniformly across the loop, then the magnitude of its internal angular momentum, which is its spin, is just m times the circulation velocity times the perpendicular distance to the loop's center, r. From classical electrodynamics, the magnetic moment of a current loop is defined by the current times the area enclosed by the loop. We can relate the magnetic moment to spin through this term. Since both mu and s points in the same direction, out of the plane of the loop by the right-hand rule, we have. Thus the proportionality between the two vectors is established. Now we can shrink this loop back into a point while maintaining the values of these quantities. More accurately, this magnetic moment must be modified by a g factor. For the electron, this is approximately 2, and for the proton, this factor takes into consideration the relativistic effect of the electron's motion, while for the proton, its internal structure, since it is composed of quarks. In fact, there can be further small corrections to this factor due to interactions which can be calculated with quantum field theory. An important point to note is, the larger the mass of the particle, the smaller its magnetic moment. This explains the smaller effect of the hyperfine structure when compared with the fine structure, since it includes the magnetic moment of the proton, which is much heavier than the electron. As we have said, the magnetic moment itself generates a magnetic field, which can interact with the magnetic moment of another particle. This is the origin of the spin-spin coupling between the electron and proton in an atom. Once again, we can use the relation between the total spin and the individual spins to rewrite this expression. As with our earlier examples, all these operators share the same set of eigenstates. Therefore, they could be replaced by their eigenvalues. Now the total spin. Using the rule for the addition of angular momenta, S of E plus P can only occur within this range. Thus we have again a doublet of states. The energy shift due to the spin-spin coupling is therefore different for the two states by virtue of this term, dependent on the total spin. This effect can be used to explain the splitting of energy of a level in the hydrogen spectrum that is not due to the fine structure or the lamp shift, since both states share the same quantum numbers L and J of the electron's angular momenta. This is the case when both states occupy the 1s orbital. We have a J singlet because L equals 0. The splitting occurs in the absolute total angular momentum, denoted by F, which also includes the spin of the proton. Note that because the orbital angular momentum of the electron is zero, the relevant interaction for this case is effectively due to the coupling of spins between the electron and the proton. The photon emitted in this transition has an energy that is roughly the same order as the lamp shift and is one order of magnitude smaller than the fine structure. This is one of the most ubiquitous signals in cosmology and is the famous 21 cm hydrogen line. 21 cm is its wavelength, which is in the microwave spectrum. This radiation originates from the hydrogen-rich centers of galaxies and is able to reach us through light years of interstellar dust due to its long wavelength. If you like this video, consider giving it a like and subscribe to this channel to get notified whenever a new video is ready. See you next time, and thanks for watching.